All right. So let me make sure this is running. All right. So, thank you everyone for joining. I hope everyone's staying warm. As you can see, I'm streaming from home. We got the winter storm. So, let's get into our statements lecture. First things first, with the winter storm, with all the university events canceled, this lecture, I don't want to say it's not mandatory. I mean, it's a precursor for all the stuff that we have to do later. But I am going to be covering, I'll recover a bunch of the stuff we talk about today in our next lecture, assuming we're back in person. And that way, if you're without power or something, then you won't really miss anything big, and you can refer back to this video in the future to actually implement everything that we're talking about. That's my dog right there. Let me take that off, yeah. All right, so let's get into it. So the current state of our compiler is that we can compile arithmetic expressions to LLVM, and then we pass that LLVM file straight to the Clang compiler, which gives us a binary, which we can then execute. We can see that in this example right here. We've got this test1 file, arithmetic expression. We run our compiler on it, spits out test1.ll, and then we use Clang to compile that into a test1 binary, which prints out the value of the expression. And so that's cool, and that's a pretty good way to start out. However, there are some limitations. We only have one arithmetic expression per file. We can't do more than one, which stinks. And then the other thing is that our expressions are kind of like auto-printed. In this language that we have right now, it's just implicitly saying that if you type in an arithmetic expression, it's going to print something. And maybe in some languages that's okay, but in C, C is very explicit in everything that it does. So we want to modify our language so that it better reflects the notion that to print something, you have to explicitly print it. That way we don't have any hidden meanings behind any of our expressions or anything like that, which is not in the spirit of what we're trying to do. And then after this lecture, that's going to be kind of the final groundwork set up for implementing more complex expressions in the future. So let's get into it. Let's look at some of the changes we're gonna plan on. So we want to modify our language to support print statements that look like the word print followed by our arithmetic expression followed by a semicolon. And that's not what C looks like. There's no print keyword like this in C. But we're going to fix that later. Right now, again, we just want to implement statement parsing, and we just want to lay the groundwork for implementing more complicated stuff in the future. For example, in the next assignment, we're going to start doing variable assignments, which is really cool. So we're going to need to add a print token type and a semicolon token type. And then we're also going to have to modify our parser so that we can check for multi-length tokens, because we haven't done that yet. All of our tokens are either, well, we sort of have with our integer literals. Those can be multi-length. But that's a very specific purpose. We wrote a specific function to parse in integer literals, but our tokens are all binary arithmetic operators. So those are all one token or one character long tokens. So we will need to add in a function to check for multi-length tokens, and we'll also need to modify the expression parser to not stop scanning and parsing at the end of a file, but rather at the end of each semicolon, and then it'll have to return that AST, and then that way we can do multiple statements per file. And then finally, we're going to do some structural changes to combine the statement parsing and the LLVM generation. We're probably going to undo those changes eventually, but right now they make sense. So I say let's do it. So this is a little BNF update. So we've still got our recursive arithmetic expressions that we talked about a few lectures ago. But now we've got this statement rule and this statements rule. So our statement is just going to be print expression, some expression, and then a semicolon, just like we said in the last slide. And then our statements, this is going to be our root rule. So our program will get parsed starting with this statements rule. A statements can either be a statement, so just one print expression, or it can be a print expression, which is that statement right there, followed by more statements. So this, you can kind of imagine it's like a linked list where you've either got one node or you've got a node with another node attached onto the end of it. So that's not too complicated, thankfully. And so let's look at our scanner updates. And let me pull this up in another window over here. So normally I've started out with saying, let's look at what's in echo/echo.py, because that's our main file. But we're pretty familiar with the structure of the project right now, and we've already planned out exactly what we're going to do. So let's just look straight at the scanner. Let's go to statements, echo scanner. All right, so, not echo scanner. Let's look at echo token. So we've added in our print keyword, and we've added in our semicolon token. I did add these functions right here, from string and string values, which you'll see how we use those later. I'm pretty sure we covered these already. So again, real trivial to just add in another token type. And remember that the string value that we put here, except for the case of like integer literal or unknown token or EOF, these strings are what are being checked by the scanner. And so that's just a nice way of keeping all of our data hooked up and not writing any extra code or any repetitive code. So let's look at the scanner.scan file or function. So this looks pretty different from the last version. In fact, it's different enough that I want to I can just look at the, no, I'd rather have them open in adjacent tabs. So in our previous scanning implementation, remember we would get a list of possible token types that a character could belong to. If there were no possible token types, we would check if it's an integer. Otherwise, we don't know what it is because we haven't added any other things it could be. If there's only one possible token type, then it's obviously going to be that one. And then otherwise, I just wrote pass here. And I realized this is a bit cumbersome, at least for right now, and so I drew it back a little bit, reduced that complexity. So let's look at what happens now. So check for end file. That's simple. We get this possible token type. Remember I said we had this from string method, and so basically what that does is you give it your one character, and let's look straight at it. From string, so you give it a character, and then for each token type, it's just going to check, is that character literally the exact same string as the token type's value. If not, then it'll give you an unidentified token or something. Oh, why are we back on the project base statements? minutes. So we've got our possible token type, and it's only going to return, this is only going to return 1, so that makes things a little easier to deal with for now. Again, if we have some unknown state, we're not sure what token this character would belong to, we check if it is a integer, and then if it's not an integer, this is our new case. We're going to check if the character is alphabetic, so A through Z, case insensitive, or it's an underscore. Those are going to be our identifier rules, at least in Echo. And eventually we do add numbers in as well. But it's important to know that, you know, in C-like languages, usually you can't put a number as the first character in an identifier. So this C is always guaranteed to be the first character of an identifier, which is again just a multi-length token. So if the first character of that identifier is alphabetic or it's an underscore, then we're going to go into this case, we're going to scan an identifier. So let's look at the scan identifier function. And we say, while the character is alphanumeric, so we add in the numeric case, or it's an underscore, we're going to add the character that we're currently looking at into this identifier string. And then we're going to grab the next character from the input stream. So this is why it's always guaranteed. This is why C in scan right here, if it's part of an identifier, it's guaranteed to be the first character of an identifier, because this while loop right here is going to process every character in the identifier until it reaches something that is not alphanumeric or an underscore, which, you know, so if you hit a space or a semicolon or something, it's going to break the loop and you'll be good. I did add in a length maximum. Other implementations of C do not have 512 as the maximum. Some have much higher, older versions have much lower limits. But it makes things simpler a little bit in the future when we're dealing with hash functions, when we add in an identifier table. So I just put that in there for now, but it's not a big deal. And then we're going to put this character back into the input stream, because when this while loop breaks, we know that C is either not alphanumeric or it's not an underscore, so it must be a number or a semicolon or something like that. So we're going to put it back into the stream so that scan can look at it later. And then we're going to return our scanned identifier. Again, just a string, nothing crazy. So we're going to say if our identifier is in token type.string values, and again, we could do from string here, but string values I think is going to come in handy in a little bit, in a few lectures. If our scanned identifier is in one of the token types, then yeah, we are going to put it through from string. And then otherwise, we are going to raise a syntax error because we've hit some multi-length token that we don't understand yet. Alternatively, you could put this through from string, and then from string, if it doesn't recognize it, would return an unknown token. So you don't really have to do this if check. You could do it the other way around, where you just process the incorrect value from string and then throw the error. But anyways. And aside from that, it is the same. So that's how we're going to be scanning in our identifiers, and for right now we've just got one, and it's the print keyword. But eventually we're going to have like 4 int struct. Those are going to be processed by this scan identifier function, and then eventually our variable names like x or count or something. Those are also going to be identifiers, and so those will also be processed by this function right here. Let's see what's next. So let's look at our expression parser. Echo, not project base. Parsing expression. And And again, I'm going to open it up and we can look at the old version. So old version, this is the Pratt parsing that we implemented 2 lectures ago. And now, again, it's about the same, but we've replaced our end-of-file checks, or we've supplemented them in some cases or replaced them with semicolon checks. So here we check both. We want to know if it's a semicolon and it's an end-of-file. In the case where it's an end-of-file here, we were expecting a semicolon, or we were expecting something else, and I just wrote this custom error right here to check for a semicolon. They say that one of the harder things about writing compilers is not just telling the programmer that they did something wrong, but exactly what they did wrong. And so you'll see in a lot of recent Python updates that the error print system has been overhauled to provide better messages for programmers. So that's what we're doing here. We're just saying, hey, I expected a semicolon, but I got an end of file. So that would replace some weird esoteric error we might throw. And again, so normal Pratt parsing, we haven't changed any of this. And then we get to, after we've parsed a binary expression recursively and we join it with the left node. If we find a semicolon, then we're good and we break and we found the end of the expression. Otherwise, if we hit the end of file, again, we were expecting a semicolon. And I also added a check up here in parse terminal node. So again, nothing really crazy there. It's all the same logic, but we want to check for semicolons instead of end of files. But now we want to parse statements. So statements are a bit different, and they're going to add another layer onto our parsing section. But because our statements are really easy right now and really simple, we only have one, our logic is going to be very simple. But eventually, this parse statements function is going to be filled with a bunch of if-else statements because we're going to have a lot of different statements that we're looking at, while loops, if statements, etc., etc. So this function right here is implementing that statements rule, the root rule of our program. So this is kind of going to be the entry point of our parser from now on. And so as long as we haven't hit the end of file, what we're going to do is we're going to match a print token. And I wrote this match function right here, which just says, as long as the current global token type matches the one you gave me, then I'm going to scan a new one. Otherwise, I'm going to throw an error because I was expecting something. So if we didn't have a print here, if we just put in one of our old files that just had the binary expression, we would get a syntax here where it said expected print, but got I guess it would be an integer literal token type. So we match a print token, and again, this function scans in a new one for us. We parse our binary expression, and we get this AST out of it. We match a semicolon token, and then we're going to yield this tree. And so if you're not familiar with the Python yield keyword, this turns our function into a generator function, which you can see up in the type annotation up here. And what a generator function does is it returns values over time. So consider the built-in range statement, for I in range, and you give it a number. That's how standard iterative loops are done in Python. And that's not actually spitting out a list back at you. It's returning a generator object, which every time it's asked for a value, it'll give you a new one. Or if you ask it for one when it's giving you all the values it can, it'll throw an error or something. But in our case, why use a generator? So we want to use this kind of lazy computation where we only give it an AST when someone calling parse statements asks for it. Because consider, farther down the line when our programs are much bigger, and we have, say a million line long program, the AST for that program is going to be enormous. And so we want to parse our statements one by one, so that we can, so that we don't run out of memory, basically, while we're parsing everything. So a generator function is going to allow us to circumvent this. Eventually, we're going to switch it to something else. We might, haven't decided yet, but if we do some optimizations across statements, then we will have to. Or perhaps we could pull 10 statements at a time, or every statement in a function, and then optimize recursively there. Wish we could do that. So the issue with this is that the call to parse statements has to be inside of our generate LLVM function. Let's look at that. If we got all of our ASTs in a list, or sorry, wrong one. We want translate.py. So you can see inside of generate LLVM, we parse our statements, and then for every single root that we get out of it, we're going to generate all this LLVM. And once we stop receiving these ASTs, we're going to generate our post-amble. But so if we did get all of our ASTs at once, and we still can, we can use the generator like a function that returns a list. We would have to just kind of restructure stuff, and again, we might in the future, but I think this makes sense for now. And so this acts very similar to how we were generating LLVM in the previous lecture. We do some stack allocation based on whatever binary expression that we give it. It's going to convert our AST to LLVM. It's going to return a print virtual register, which contains the value, the integer value of the expression that we gave it. And we're going to print it out, and just implementation error, we have to bump up our virtual register number because when you call, there are some statements in LLVM that expect you to assign their value to a virtual register, even if you don't need it. So, for example, when we call printf, which we do in LLVM, it has a return value. It returns an I32, which just tells you whether the printf was successful or not. But even if you don't assign that output to a virtual register, the compiler internally expects that you do. And so because we don't, we have to manually bump up a virtual register number to account for the register we would have used when we assign the output of the printf call to a virtual register. So lastly, all we have to do is go over to our main function. And so this is why I kind of wanted to work backwards, because I think it made more sense to go from the inside out. All we've changed here is that we replaced our call of parsing our binary expression and then passing it in and generate LLVM. We just replaced it with generate LLVM, because that's going to do all of our statement and expression parsing inside of that function from now on. And that's it. We've done it. Let's just take a look at that behavior. Just make sure I'm on the latest. Okay. So out test1.ll. So this is our new examples test1 file, and we've got two print statements here. So this is the one that we had before, and I just added another one right here. And you can add 100 print statements if you want. But let's run it through our compiler. Scripts run examples test1. And so that's going to spit out a test1.ll file. And look at all that. So this is our two expressions that have been generated. So our first one, 2 plus 3 times 5 minus 8 over 3. So that's got 1, 2, 3, 4, 5 integer literals. We allocate 5 times. We store in our values, and then we do the necessary operations on them. So on and so on. And then finally we call printf on register 14, which has that overall value in it. And then we start over. We do it again for this next statement that requires 3 integer literals. We allocate 3 times, we store, we load, do arithmetic, and then we call printf again. And so that's that. Let's see how it works. Claim test1.ll minus o test1. Let's call the test1 binary. Boom. And just for confirmation, let's see if Python agrees with us. So 2 plus 3 times 5 minus 8, integer division 3. We said it was 15. Python says 15. And then we've got 1 plus 35, integer division 2. We said 18. Python says 18. And so that is that. That is the entire... that was a pretty short lecture, right? But adding in that statement parsing allowed us to... it's going to allow us to do cool stuff later on. So I am very excited to get into assignment statements, because that's when it starts feeling like a real programming language, when users can come up with their own variable names and stuff, and it's very cool. Very excited. I hope y'all are excited. And so let's talk about the optional homework. This week's optional homework is to implement just some kind of complex mathematical statement. And I want you to, update your parser and compiler accordingly. The only requirements are that your statement has to take in an integer value as input, and that the AST generated by the statement must be a complex expression. So, for example, you could write a statement that computes like Fibonacci. You give it an expression, semicolon, and that would print out, for example, the nth Fibonacci number. I would suggest in that case that you do your Fibonacci logic inside of the compiler. So you would generate that n into an AST that reflects the math behind computing Fibonacci numbers. Don't write a Fibonacci function in Python that spits out the value, the nth Fibonacci value, and then print it, because that's boring. I want you to generate an AST that is, for Fibonacci 5, it would be like print 5 times 4 times 3 times 2 times 1. That's what I'd want it to equate as. Yeah, it has to be complex. Don't give me square n where it prints out n squared. That's too easy. Think of something cool. Again, it's optional, so if you don't like this one, don't do it. But that is all I've got. I'm going to check the Discord. I don't see any questions. I don't see any questions on the YouTube Live. So that's that. If you have any questions, email me. Again, I'm going to be very briefly covering this material when we come back to class in person. So if you feel like, if your friends don't have power or something, they should be good. So thank you, and stay warm.